Hey, what's up? It's your old pal, Mr. Cook, and we are going to work on the Unit 6, Part 2 group work. So we just got through the first page, which we're going over a lot of definitions and little equations and things like that, and the unit circle. On the second page, we're going to focus mostly on just graphing and the different parts of the transformations that take place from your typical trigonometric function. So speaking of that, your typical trigonometric function always starts off like this. Y is equal to, and then your sine function or your cosine function, any of these trig functions. All right, so if some number is multiplying on the sine, that's your amplitude. That's basically like the amplitudinal value going up and down from some central line that the graph is rotating, or not rotating, I shouldn't use that word, that it's reflecting around or it's symmetric about. And that central line can be found really easily by whatever number is adding or subtracting outside of the sine or cosine or secant or cosecant function. So this tells you the amplitude, and the amplitude is a y, change, a shift in the y direction. The d value is actually a vertical shift going up or down. So this is also going to tell you the central line, which is the center graph part, which is also part of your y-axis. Your entire x-axis can be found inside of the sine or the cosine or the secant or the cosecant. And it's typically written up like just as a linear equation. That's how we're going to stick with in this class. Now this b value that you have changes the period. Now the period is like in a sinusoidal pattern, it just like continues on and on and on. It's just oscillating like a little wave. Well, one little section of this pattern. So if I started here and then ended it right over here, this is the length of one period, okay? The period is the x distance that one pattern takes place. So if I took this and cut it out and then moved it over here, you see it would be like the same exact pattern. Well, this would be the same exact distance, the period distance away. These values are always going to be the same for sinusoidal functions, and it's always like basically the same, one pattern's distance, in the x direction. That's how you describe a period. And that b value tells you where the period is going to be. The c value here tells you about phase shifts. Phase shifts are just taking the graph, not changing the period, but just moving the graph to the left or to the right along the x-axis. So this is going to be where you can find your phase shifts. I'll show you how to get all of this stuff, and I recommend looking at the extra review because that's where I'm going to be able to go through a lot of graphs, and I think that I'll probably even section that off like accordingly, just the graphs themselves on one video. Anyways, let's look at the individual little parts of it. To find the period, it's really easy. For sine, cosine, for secant, and also cosecant, the period, like the standard period, the length of the period for the sine, the cosine, the secant, and the cosecant, if you're talking about degrees, it's going to be 360 degrees. If you're talking about radians, it's going to be 2 pi radians. Now, the b value changes that up. So what you can do is think about it like this. Any number that's multiplying on the x value, all you need to do is just divide that number into either 360 or 2 pi, depending on if you're dealing with radians or degrees, and that'll give you the period. That will find you the actual length of, in the x direction of one of these patterns. That's what the period represents. Tangent and cotangent are just a little bit different in that they just, the pattern itself repeats in a standard way over a shorter distance. So tangent and cotangent, if you look on your unit circle, tangent repeats its pattern after just 180 degrees or pi radians. So that means that for tangent and cotangent, we just take those two values and divide it by the b, and that will give us the period for those two, tangent and cotangent. They're pretty easy to deal with, but you just have to remember that one little part of it. So tangent and cotangent are pi and 180. Sine, cosine, secant, and cosecant are 360 or 2 pi, one full circle. Okay, so the first one asks us to find the period, but it doesn't specify for part A whether or not we're dealing with degrees or radians. So I'm going to find both for you. The number that we need to first find the number that's multiplying on the x, that b value. So to find that, we just ask ourselves, what number is multiplying on x? So x over 3 is the same thing as saying 1/3 x. So that means that 1/3 is our b value. So if I take 360 and divide by 1/3, when you divide by a fraction, it's the same as multiplying by the reciprocal, so 360 times 3 would give you 1,080 degrees. So that's the length of the period in terms of degrees. If we're talking about radians, then it's going to be 2 pi over 1/3. And again, 2 pi times the reciprocal, so times 3, would be 6 pi. So these two are equivalent lengths of the period, just in different units. One's in degrees, one's in radians. So quite similarly, we can do part B. So part B, the number that's multiplying on the x value is just 1, so that's our b value, 1. And since I have this pi over 2, I happen to know just kind of implicitly that we're talking about radians only. So that's I'm just going to do the radian value, 2 pi over 1, and then 2 pi over 1 is just 2 pi. So the period length is 2 pi radians for number 9b. So that's how you find the period. Really, really easy stuff. Make sure that you know how to do that, and make sure you know this stuff as well. Finding the amplitude is going to be really easy as well. Now the amplitude on sine and cosine is the distance that it goes from this central line where it's symmetric, and it's just the length that it goes from the central line to the peak value. And it's always going to be the same number if it's going up an amplitude or down an amplitude. It's the same number. And you can find that number real easily from whatever number is multiplying in front of your sine or your cosine or your secant or your cosecant or your tangent or your cotangent. For those last four that I mentioned, secant, cosecant, tangent, and cotangent, the amplitude basically works like a vertical stretch or a vertical compression, just like how we learned about the function transformations earlier on, and less like an amplitude. You could argue that it kind of does work like an amplitude for secant and cosecant, but it's not values that you can attain from the central line. Like these are actual like maximum and minimum values. They're max and minimum values, and you can attain them with secant and cosecant, but it more like describes the negative space that you have in your graphs. And we'll see that when we graph out a secant a little bit later on. But anyways, to find the amplitudes is just a number that's multiplying in front of the sine, or the cosine, or the secant, or the cosecant, or the tangent, or the cotangent. In this case, it's just 1/4. Don't include negatives, just positive. That's all that we need for the amplitudes. And then 2 for the cosine. So pretty easy stuff. I'm going to actually jump from here to our graphs. Okay, I'm going to skip this part where we do the domain and the range just for a second, just so we can see how it looks graphed out and talk about what the domain and range look like on a graph, so you can kind of visualize what it's going to be. Okay, so I can pick out a couple of things from here. I already know that like the amplitude I can list off pretty easily because I just did amplitude back here on number 10. Amplitude is the number that's multiplying in front of your sine or your cosine or your secant or your cosecant. So in this case, it's just a half. In this case, it's 2. And then the reflection part of it just means, do you have a negative on your amplitude? In this case, I don't, so I just write n for no. And then in this case, I do have a negative, so yes, I do have a reflection on that secant function. The next thing I'm going to list off is the vertical shift. The vertical shift can be found by just seeing whatever number is adding or subtracting outside of the sine function or the cosine function, as it might be. In this case, we're just adding on 5, so that means that my vertical shift is 5, and then it's 2 over here. Now, since these numbers are positive, it means that my vertical shift is up 5 and up 2. If it was a negative number like -5, that'd be down 5 instead. And this gives you, along your y-axis for your graph, that middle number, that 5 that goes right there in the middle. Same thing here, it gives you the 2 that goes in the middle. So this number that's adding or subtracting at the end is going to go in the middle of our graphs. And the amplitude helps us because that helps us to establish our y-axis. So for this one, since it's a 1/2 amplitude, it's going to go up by a half, so 5.5, and then up by a half again to get to this next number. So 5.5 plus a half gives you 6. 5 minus a half would be 4.5. And if I subtracted another half, that'd be 4. The amplitude on this one is 2, so I go up 2 to 4, and then up 2 again to 6, and then down 2 to 0, and then down 2 again to -2. So that creates your y-axis. Now, the reason that I wanted to skip this part is because we're also set up to write in the period, and therefore get the x-axis completed over here pretty easily as well. So find the period for this function. So the number that's multiplying on the x, and by the way, this little theta here, that's the same as an x. Don't get confused with that. It's the input value for this, okay? So the number that's multiplying on the x is that 2/3. So since I'm dealing with radians here, I'm going to keep in terms of radians. So 2 pi divided by that number, 2/3. That's the same as multiplying by the reciprocal. So 2 pi times 3 over 2. The 2's cancel out, and I'm just left with 3 times pi. So 3 pi is my period. For this one, if I were to take that 3 that's multiplying on the x and divide it by the 2 pi, because I'm probably going to be dealing with radians because I have that pi over 2, it's just 2 pi over 3. I can't reduce it any further. That's the period for that function right there. All right, now let's get the phase shift and the x-axis all done. It's pretty simple stuff. All you need to do is just take the function inside of the parentheses and set it equal to two different numbers. So 2/3 x plus pi fourths. I set it equal to 0 to find the first number here, all right, on my x-axis. And then I take that same equation and I set it equal to 2 pi to find this last number here. And I'm going to do the same thing over here, those equations, 3x plus pi over 2, set it equal to 0. And since I'm dealing with secant, which has a period of 2 pi, I'm still going to set 3x plus pi over 2 equal to 2 pi. Now, you just got to trust me on this. If you set it equal to these two numbers, then that means that these x values will be found, and they'll add up to the period. Like, you know, it'll be this length across here, 3 pi from here to here, if you do this correctly. So now let's practice this and find out what those beginning and ending values are. So to get x by itself here, I got to subtract pi fourths. So I get 2/3 x is equal to negative pi fourths. And then to get rid of this times 2/3, you just multiply by the reciprocal. So times 3 over 2 on both sides. So that means that my x value, my starting value over here, is going to be a negative 3 pi over 8, because 4 times 2 is 8. All right, so that's the starting amount. And then let's find the ending amount over here. So solve again, subtract pi fourths. I get, let's see, that'd be 2/3 x is equal to, and then 2 pi minus pi over 4 is going to be 7 pi over 4. And if you struggle with adding and subtracting fractions, you can always use your calculator for this. You know, just to kind of show you, I'm going to get the same number, 7/4. Ready? So I take 2 pi's, or just 2, and subtract away pi fourths, or 1/4. You basically just leave the pi out of it. You get your decimal and then convert it to a fraction. It'll give you a reduced fraction, 7/4, that you use by just multiplying a pi on it at the last second. So 7 pi over 4 is our last number over. Oops, I'm not done yet, am I? So 7 pi over 4 is equal to 2/3 x. So to get rid of that 2/3, I multiply both sides by the reciprocal, 3 over 2. So 3 times 7 is 21, so I have 21 pi over 4 times 2, which is 8. Okay, so this is the beginning amount and the ending amount. Now I got to fill in the rest of these. These are all going to be evenly spaced, so it's actually really, really easy to find these just by adding or subtracting your fractions. But, you know, if you want to fast forward through it, you can just use your calculator, because all you need to do is just find the average of these two fractions. So I will show you how to do that. So to get this middle value, find the average of these two fractions. But again, leave the pi's off of it. So all you need to do is negative 3 over 8, so negative 3/8, plus this fraction, 21 over 8. So that adds them together. And then how do you complete an average? You add the two together and then divide by the number of numbers, which is 2. So that gives you some decimal answer, turn it to a fraction, and that gives you your middle value, which is going to be 9 pi over 8. Now just repeat the process over here. So take this fraction, negative 3/8, plus this fraction, 9/8, divide it by 2, and then turn it into a fraction. So that gives you this middle number, which is going to be 3 pi over 8. Now let's find this middle number. So I do 9 over 8 plus 21 over 8, divide it by 2, turn it into a fraction. So this is going to be 15 pi over 8. So if you hate, adding, subtracting fractions, trying to do all that stuff by hand, like, this is the way to do it. So just make sure that you practice this. It'll, you can practice along with me over here. Just make sure you got the steps right. Anyways, this also helps us to establish where the phase shift is. So typically your sine functions, cosine functions, secant, cosecant, tangent, cotangent, all should have 0 for the first x value. But this one doesn't. It has negative 3 pi over 8. So how far away is that from 0? So on an x-axis, if I had 0 here, how far away is negative 3 pi over 8? It's 3 pi over 8, distance, and it's in the negative direction, so to the left. So your phase shift is left by 3 pi over 8. That's all that you need to do to figure out that phase shift. It should start at 0, instead it's negative, so to the left. So left, 3 pi over 8. You can do the same thing for the phase shift in the x-axis over here. So I'm going to write up the x-axis as well real quick. So solving this one, 3x plus pi over 2 equals 0. If I subtract pi over 2 from both sides, I get 3x equals negative pi over 2. Then if I divide both sides by 3, I get x is equal to negative pi over 6. So that's going to be my very first number that I put on the x-axis, negative pi over 6. I'll make sure I have that negative more established so you can see what I'm writing. There we go. Now I'm going to do the same thing here, subtract pi halves. So I get 3x is equal to 2 minus a half, which is 3 halves, so 3 pi halves. And then I divide both sides by 3, and I get x is equal to pi over 2. So pi halves is my number over here. And then I just do the same little trick that I did on my calculator. Add the fractions, divide by 2, turn it to a fraction. So negative 1/6 plus 1/2, divide by 2, and then turn it to a fraction. So 1/6, so pi over 6. And this one should be obvious, right? What's halfway between pi 6 and negative pi 6? Right in the middle is 0. And then do the last one. So we have 1/6 plus 1/2, divided by 2, and that's 1/3. So this should be pi thirds. I don't even need to convert it to a fraction there. And there's all my x values. Now it's right in the phase shift. It should start at 0. But instead it moves over to negative pi over 6. So that's to the left by pi over 6. Okay, now for the rest of the graphs. So sine has the same pattern every single time. It starts in the middle, goes up in amplitude, back to the middle, down in amplitude, and then back to the middle again. And then there's no reflection, so I just leave the points as they are. And then since it's sine, I just draw in the graph as best I can. Remember that it's got a little bit of curvature to it. Don't just draw linear lines going straight through all the points, because it'll look kind of weird and not very sinusoidal. All right, so there's our sine graph, and we are good to go with that one. Now let's do the secant. So secant is related to cosine, so we graph out the cosine function. That's the starting point. So cosine starts at 1 on your unit circle, so that means it starts up in amplitude, and then it goes to 0, and then it goes to -1, and then it goes to 0, and then it goes back up to 1 to complete the circle. Now, that would be a typical cosine, but you know that we've reflected it. So over this little central line, we reflect all of those points. So this point gets reflected downwards. So it's going to go down here. This one gets reflected over that central line, so it goes up to the top, up 1 amplitude. And then this one that was up in amplitude gets reflected over down here. Now, since these are reciprocal relationships, there's going to be obviously some undefined values, some x values that you, some secant values that you can't find, because if you have some cosines that are zeros, the reciprocal that'd be 1 over 0. So that's why like all these points that are in the center become vertical asymptotes. So you can just draw a dotted line through those little central points. And then the ones that have like the minimum and the maximum amplitudes, those are just going to turn into kind of like parabola looking shapes, but parabolas can continue on to the left and to the right. So I just call them that's why I say parabola-like shapes, because they look like parabolas, but they actually fit inside of these vertical asymptotes forever, so they aren't quite parabolas. All right, so continuing on with the rest of the graph, this one goes straight down, this one goes straight down also. That's just because we didn't continue on with the pattern, but otherwise it would be more little parabolas facing downwards like that. Okay, so that's our secant function, and once again, if you want more practice with sine and secant and all that stuff, you can go back to those old packets that we did, and then also the extra review. I think I've done a couple extra graphs on there as well. I think there's 8 or something like that on there that I went through. Okay, last couple problems. So let's go back over to the domain and the range. For cosine and also for sine, there's no vertical asymptotes anywhere. There's no limitation as to what you can plug in terms of the angle measurements. You can plug in negative numbers for your angles. You can plug in positive numbers. You can plug in 0. You can get anything. So that means that the domain, there aren't any restrictions anywhere. So it'll be all real numbers for cosine and also for sine. We'll have restrictions on secant and cosecant because of these vertical asymptotes. And actually, when you graph out tangent and cotangent, those have vertical asymptotes as well. So they also have domain restrictions. But you don't have to worry about those because, if you wanted to write out the domain for those, we need a sequence, and we don't want to have to go through the trouble of, going through all that stuff. Save that for when you're in calculus or AP calc or whatever. But anyways, so the domain for both of these are just going to be all real numbers, easy stuff. Now we go over to the range. So the range can be found for sine and cosine based off of just these two numbers right here on your graph. So imagine you have your central line, and then it goes up and down by the same amount. So all of your y values are stuck between these two lines right here. So these two points are going to give you the restrictions on your range, how far it goes up and down in the y direction. So let's kind of like reason what that would be like over here. So this +4 would give you that little central line that we have from our transformations, and the amplitude goes up and down by 1. So like if you think about it, the graph kind of looks like this so far. In the middle is 4, and then it's going to go up and down by 1, so it'll go up to 5 and down by 3. And then since it's cosine, it'll start up here, go to the middle, and then go back up like that. So that means that all of our y values are restricted from 3 to 5. So to write that out, just as an inequality, your y value is going to be between, and because it actually gets to this point, so it'll be including, so that's why we have those little equal signs there. It'll be between 5 and 3. If you want to write it out in interval notation, it just looks like this. So you can write either of these answers and that'd be okay. Interval notation goes from 3 to 5. So either of those, good enough for the range. All right, do the same thing for your sine function. So the central line is going to be at -1. So on your little graph, the middle number is -1. And then the amplitude here is 4, so it'll go up and down by 4. So if I take -1 and add on 4, that gives me 3. So that means that the sine is going to go up to 3. If I subtract away 4, that'll be at -5. So sine starts in the middle, then it goes up and then down and then back up like that. So all my y values are going to be between 3 and -5. So similarly, I'd write up -5 less than or equal to y, which is less than or equal to 3. Or in interval notation, it'd just be from -5 to 3. And that'd be my range. So either of these would be fine if you wrote those down on your test. Okay, so we have one last group of problems, and that's going to be the inverse trigonometric functions. A lot of these are pretty easy. You just need to know the domain and the range, since they're functions now, that lead us to exactly one y value for every one x value that we have for sine and cosine and tangent. So for sine, if you remember, we only allow you guys to use the first and the fourth quadrants for the range values, because this tells us that when we have this domain, like all of our positive signs are going to be in this first quadrant, and all our negative signs are going to be in this fourth quadrant here. And that also means that we have to split up what the range looks like. So the range of angle measurements that you can have, they go from pi halves or 90 degrees to negative pi halves or negative 90 degrees. So your answers just need to be between those two when you answer them out in radians. So which angle measurement has a sine that's negative square root of 3 over 2? Well, your sine values are going to be positive in the first quadrant and they're negative in the fourth quadrant. So obviously, if our sine is negative, it's going to be in the fourth quadrant. All right, so fourth quadrant. And if you look on your unit circle, which of the angles has a sine of negative square root of 3 over 2? If you looked on your unit circle, you should see that that coincides with the angle measurement 5 pi over 3. Okay? So 5 pi over 3 is not in the range of pi over 2 to negative pi over 2. So what is the angle that you're looking for? The angle that you're looking for is going to be this angle that goes right over here, the reference angle. But it's going to be a negative reference angle because it's going negative in the negative direction. So what is this little angle measurement right here? So this 5 pi over 3 is pi thirds short of being a full circle. So that means that this angle is pi thirds. If you need to convert that into degrees to make sense of it, go for it, because this will be like, hey, that's 300 degrees. This is 60 degrees. It's 60 degrees from a full circle. And then just one more time, remember that it's going in the negative direction because it's headed down this way. So this is going to be a negative pi thirds for my answer. All right, now let's move on to cosine. So cosine is defined over the top two quadrants. So cosine's positive in quadrant 1, cosine's negative in quadrant number 2. It's because of the x values, right? It's positive in the x direction, negative in the x direction, pointing to the left there. Now, cosine inverse of 1/2 means that the cosine is going to be positive. So that happens over here. And if you look on your unit circle in quadrant number 1, you should have a cosine of 1/2 over here at pi thirds. And luckily, pi thirds is in the range that we're looking for, because for cosine, it goes from 0 all the way over to 1 pi. So our answer of pi thirds works out. So the answer on your unit circle is the answer that we're looking for, pi thirds for that. Okay, last couple problems. Tangent inverse of cosine of pi. Please make sure that you do this part first, inside the parentheses. So if you just look on your unit circle, cosine of pi should give you -1. So this is really looking for the tangent inverse of -1. So tangent is very similar to the way that we define sine. and that it has a positive tangent values in quadrant 1, negative tangent values in quadrant 4, and once again we go from pi halves over to negative pi halves. The only difference is, since both of these give us undefined values, we actually don't include pi halves or negative pi halves. But that doesn't matter for this problem because the tangent is negative in quadrant 4, and if you look on your unit circle, it actually coincides with, let's see here, that would be 7 pi fourths, which is how far away from 0? It's going to be this distance, which is pi fourths away. So the answer for this one is going to be negative pi over 4, or negative 45 degrees. All right, so that's our answer for this this problem. Now we go on to the last one. And if you remember how to do these from our homework, when we have an inverse trigonometric function inside, this tells us how to make our triangle. So cosine inverse, once again, is going to be first quadrant or the second quadrant. Since this is a positive cosine, it's going to be in the first quadrant, so we draw out our triangle. So here's our first quadrant, and then we just draw a right triangle with respect to the x-axis, always with respect to the x-axis, because that gives us our little reference angles. Now the cosine ratio is adjacent over hypotenuse. So the adjacent side is 6, the hypotenuse is 5. And this should cause, some concern, right? Because the way that this triangle is drawn, we cannot draw a right triangle. Because look, the adjacent side is bigger than the hypotenuse. In a right triangle, can the hypotenuse be anything other than the largest side? No. It can be, it can be anything other than, something less than 6. Like you could have it as 6.1 or whatever. You can still make a right triangle out of it. But this side has to always be bigger than either of these two sides for it to be a right triangle. So since that's not the case, that means that this problem is impossible. So you cannot do this one. It's not, like an undefined value or anything like that, because you can't even make a right triangle with the information that you have. So it's not possible to do this answer. So instead, just as a bonus, we're going to do one that you can do. So let's clear out a little space. Let's do the cosecant. Or no, let's do tangent. Yeah, tangent. That'd be fun. So let's do the tangent of, and then let's do the same thing, cosine inverse of, and then let's jazz this up a little bit. Let's make it 5, 6, because we can do that. And let's also make it negative. All right, so this is going to be a challenging problem because first off, if cosine is negative, that actually puts it in the second quadrant, right? Because cosine is defined in the first quadrant and the second quadrant, and if it's negative, it's over here. So let's draw it up. Second quadrant. Here's our little right triangle. And then it's negative 5 over 6. So negative 5 is your adjacent side for this angle. So negative 5. And 6 is your hypotenuse. So now we can do the Pythagorean theorem to find that missing side because our hypotenuse is 6, and that's bigger than the adjacent side. So if we do Pythagorean theorem, let's see, let's call this side x. X squared plus negative 5 squared is equal to 6 squared. So 25 is equal to 36 plus x squared. So subtract 25 and you get x squared is equal to 11. And that means that our missing side is the square root of 11. So square root of 11, there we go. Now if I wanted to find what was I looking for? The tangent of this triangle right here. The angle has an opposite side of the square root of 11 and an adjacent side of negative 5. So that means that the answer for this one would be in our little example that we just made up. It's going to be a negative square root of 11 over 5, opposite over adjacent. And that would be the one that we're looking for there. Okay, so that's it for the second page on your group work. If you have any additional questions, don't be afraid to go ask your teacher. This stuff shouldn't be too difficult, especially considering, if you haven't noticed already, we don't have any word problems. So it's all just going to be process-oriented stuff and graphing, using your calculator, stuff like that. So make sure that you prep for this test. If you need some additional help, seek out your teacher. All right, that's it. Good luck on your test, guys.